Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today, leading off, we're going to bring on two figures in science who are leaders in their respective fields. The first scientist is Seth Shostak. He is the director of the Search for Extraterrestrial Intelligence. Now, you've probably seen on TV a number of specials about aliens from outer space. The aliens are going to invade us. The aliens are right next door watching us with their flying saucers. But what about how science views the whole question of intelligent life in the universe? Dr. Seth Shostak is a PhD in physics. He's a colleague of mine. And instead of teaching graduate students at prestigious universities all the intricacies of astrophysics and quantum mechanics, he instead has decided to devote his life to the search for alien civilizations in outer space. Now, at first you may say to yourself, wow, that sounds like a waste of time. Or, wow, maybe he's on the cutting edge. Maybe his name will go down in the history books when they make contact with aliens from outer space. Who knows? But that's what he does for a living. As the director for the Search for Extraterrestrial Intelligence in Mountain View, California, he is the man eavesdropping on radio emissions from alien civilizations, if there are any. And then in the second half of Exploration, we're going to bring on another Seth Lloyd. He's a professor of physics at MIT, and he believes in quantum computers. In other words, eventually the silicon computers you have on your desk will be exhausted. Instead of computing on tiny bits of silicon, we'll have to be computing on atoms. And that means that the CIA is interested in this because these are very powerful computers that in principle could break any code. And so in the second half of Exploration, we'll talk about quantum computers. And so once again, in the first half of Exploration, we're going to leap into the unknown with the search for extraterrestrial intelligence. Our special guest, Dr. Seth Shostak, director of the Search for Extraterrestrial Intelligence, who has devoted his life to eavesdropping on radio emissions from aliens in outer space. Maybe one day we'll pick up the equivalent of I Love Lucy being broadcast from an alien civilization thousands of light years in the heavens. Who knows? And then the next big question is, what do you do? What do you do if you actually made contact with an alien civilization? We'll talk to Dr. Shostak about that. And then in the second half of Exploration, we're going to talk to another Seth, Dr. Seth Lloyd of MIT. He's one of the world's leading figures in something called quantum computers. Well, the first guest today is Dr. Seth Shostak, and he's following in the footsteps of astronomer Frank Drake. Back in the 50s and 60s, astronomer Frank Drake had the idea of searching for radio signals from intelligent life in outer space, intelligent enough to use radio to broadcast on. But the question is, there are so many frequencies out there. Which frequency do you dial into if you want to listen in on a conversation between aliens?
Well, that's actually a good point because, of course, the aliens haven't sent us a fax telling us where on the dial they might be broadcasting. So you have to sort of second guess what frequencies, what part of the dial makes sense. And that idea had already been explored, even though Frank Drake didn't know that, by a couple of guys who at that point were at Cornell University, a couple of physicists by the name of Giuseppe Cocconi, and Philip Morrison. Anyhow, these two guys had already thought about what frequencies make sense if you're going to send messages between the stars. And they said, well, look, there's kind of a natural answer to that because there's one frequency everybody will know, and it turns out to be 1420 megahertz on the dial. You might think, well, what's special about that? It turns out that hydrogen, which is by far the overwhelmingly most common element in the universe, hydrogen naturally emit some radio emission at 1420 megahertz. So all astronomers, of any sophistication in the universe will know about this frequency. So they said, look, that's a natural frequency. Everybody will have it marked on their radio dial. Let's try listening there. Frank Drake came to the same conclusion rather independently. And so the first experiments were done usually with a receiver that only had one channel. It could only listen to one channel at a time, just like your auto radio, and set that frequency somewhere near this 1420 megahertz magic frequency on the dial. Now, as time went on, this kind of experiment became much more sophisticated. Today, the receivers that are used for SETI listen simultaneously to tens of millions of channels at once because, you don't know exactly which frequency might be the one they're using, but they tend to look at that part of the dial around 1420 megahertz. Not always. Sometimes they'll do experiments where they're looking elsewhere, but usually you're covering maybe 1,000 or 2,000 megahertz around that frequency. So, it's a small fraction of the dial, but it seems to be a pretty good one. No one's ever come up with a better argument about where to tune.
Okay, now let's talk about Drake's equation, which is taught in every elementary astronomy course as scientists try to get a reasonable scientific estimate of the probability of intelligent races throughout the galaxy. So tell us a little bit about Drake's equation.
Well, the equation actually has an interesting history, or at least semi-interesting. Frank Drake had done that listening experiment in the spring of 1960. So, gosh, that's 45 years ago. It was in April, I think, 1960. Anyhow, so that generated a lot of interest. I mean, he didn't find the aliens, but it generated a heck of a lot of interest. And so the next year, he had a meeting, also in West Virginia, at the observatory, in which he invited all the kind of professional scientists who were interested in this work. That total was like 10 or 12 or something. It was a fairly small number. And as an agenda, he was sitting around thinking, well, this meeting's coming up in a couple of weeks. I need an agenda. So as an agenda for this meeting, he wrote down this very simple equation, which has subsequently become known as the Drake equation. And all it does is try to estimate something called N, where N is the number of civilizations in our galaxy. Just let's confine ourselves to our galaxy that are broadcasting right now. So the number of star systems, if you will, that are producing signals now that we could detect. Now, clearly, that depends on, well, how many stars are there in the galaxy, and what fraction of those have planets, and what fraction of those planets have produced life, and what fraction of those that have produced life have produced intelligent life, and what fraction of those have produced technology, and what fraction of those are actually on the air right now. Okay, so it's a whole string of terms. There are actually 7 terms in the equation. You can find it in almost any textbook on astronomy, and that's the Drake equation. And it would be great because it would tell you, what are your chances of success? I mean, if N is only a few, then the chances that you'll find these guys is pretty small. But if N are thousands or millions or some very large number, Carl Sagan thought that the value of N was several million. Well, if that's true, then, you have a pretty good chance of tripping across a signal sooner or later. So, unfortunately, of course, we don't know what N is. There are a bunch of terms in the equation that we simply don't know. So it's more of a talking point kind of thing than it is an equation that you can actually solve or use.
Other scientists say, bah, humbug. We had Professor Brownlee on our airwaves about a year and a half ago, and he said that Drake's equation is flawed. Flawed because there are new astronomical bits of information that show that, to get life is more difficult than we thought. He mentions, for example, that you need a large moon. Without a large moon, the Earth would eventually tumble in its orbit and over hundreds of millions of years, and that would make DNA impossible. He also mentioned the fact that at one point the entire Earth was frozen over. We were snowball Earth. And again, DNA would be very hard to get off the ground under those circumstances. He mentions you have to have a large Jupiter in order to clean out the debris of the solar system. He also mentions you have to be a certain distance from the center of the black hole at the center of the galaxy. Otherwise, you get fried by being too close to this very radioactive core at the center of the galaxy. But if you're too far out, then there are not enough heavy elements to create DNA and higher molecules. So, well, what are your thoughts? Is the Earth in some sense unique, as Professor Brownlee was hinting at? Or do you think N is quite large, as Carl Sagan believed?
Well, of course, nobody knows, so everything I'm going to tell you is my opinion on this,
Okay,
obviously.
good enough.
If we knew the answer, we wouldn't be discussing it, but it's true. Don Brownlee and his colleague Peter Ward at the University of Washington up in Seattle wrote this book about 5 years ago called Rare Earth, in which they had indeed, as you indicated, kind of a laundry list of reasons why Earth might not be just a run-of-the-mill planet. Earth might be very, very special, so special that, in fact, although there might be some other life out there, it's not going to be very sophisticated life. It isn't going to be intelligent life. And so our SETI experiments are kind of a waste of time. That was their thesis. And since this was reviewed, by the way, in the New York Times, this book got a lot of play. And but if you actually look at this laundry list, you find that the items on it are not terribly convincing. Let's take a couple of the ones you named, for example. The fact that the Earth has a large moon, which kind of stabilizes the spin of the Earth. Okay. Now, if we didn't have that large moon, and by the way, a large moon is kind of a rare thing. Mercury doesn't have a large moon, has no moons. Venus doesn't have a large moon, has no moons. Mars has a couple of moons. You could walk around in an afternoon. Tiny moons, they don't help. Earth, on the other hand, among the rocky planets, is the only one to have a large moon. Okay. And sure, it does stabilize the Earth's spin. But if you took that moon away, yes, well, the Earth wouldn't, just go completely nuts. Every now and again, the North Pole would come down to, Connecticut or some other place, that sort of thing. But it would take hundreds of thousands, maybe millions of years to do that, right? So it's such a slow event that even for complicated life like freshwater otters or whatever, right? They can just walk away from that problem. If you've got 100,000 years, before the North Pole gets to you, you have plenty of time to move. I mean, that isn't fatal to life. That's not fatal. It might be an inconvenience, if you had a society with a lot of cities, you might not want it to happen. But it's so slow. It's not fatal. Now, here's another thing in your list there. You mentioned we're fortunate to have Jupiter because Jupiter has cleaned out the inner solar system of all these big rocks that otherwise might, slam into your planet and ruin the whole day, just the way it happened 65 million years ago, taking out the dinosaurs and 75% of all other species. Well, sure. But on the other hand, big Jupiters are not rare. We know that. In fact, all the planets we've found around other stars are like Jupiter are bigger. Right? So big planets are not rare. But even aside from that, you could argue that maybe life on Earth would have gotten a little bit farther had we not had such a big planet as Jupiter out there. Because, in fact, if the dinos had been wiped out 50 million years earlier, we would be 50 million years ahead of where we are today. We'd have the cure for death, whatever. It would be, maybe we'd be better off. So I don't find that a very convincing argument. I mean, you can look at each one of these arguments. The snowball Earth, yes, there's some evidence, although it's somewhat controversial, but there's some evidence that there was a time, a few billion years ago, when the entire Earth was encrusted with ice. But there was life on Earth then. And that life wasn't wiped out by snowball Earth. It just, had to sit there and live at the bottom of the oceans for a while, but, a lot of life, well, all life was down in the oceans anyhow. So, it didn't wipe out Earth. It wasn't fatal. Okay, so all these things, yes, they might be an inconvenience, or they might not be, but in any case, none of them stopped life on Earth. None of them stopped life on Earth. So I really don't think that Earth is really all that special.
Well, Professor Brownlee goes on, in fact, on and on and on, as I found out interviewing him. He also says that microbial life could, in fact, be quite common throughout the universe, but intelligent life, well, take a look at the dinosaurs, he says. We've had life forms with spinal cords and nervous systems for hundreds of millions of years on the Earth, but humans, only humans on the Earth, even on the Earth with such ideal conditions, it took hundreds of millions of years for humans to get off the ground, and even then, there were many times when humanity may have been wiped out. There were only a few thousand of us, 100,000 years ago to create the entire human race. The human race could have been wiped out many times during certain bottlenecks in our evolution. So he was basically saying that intelligent life is extremely rare, even if you have microbial life being common. What are your thoughts?
Well, he's right in that this is a controversial area. I think even more controversial than the question of whether you can get complex life on a lot of planets. I don't think that's so controversial myself. But just because I give you a million planets with life, right, and you let them cook for a few billion years, there is a legitimate question: what fraction of them will ever cook up something as clever as as we are? and we are clever compared to most critters around, right?
That's debatable, but anyway.
Well, but in any case, I mean, we don't know because we still don't understand fully how, or even partially really, how intelligence evolved on Earth. What was it that produced intelligence on Earth? If it's a mechanism that was just very rare in the sense of being accidental or contingent upon a lot of special circumstances, then maybe he's right. Maybe you got lots and lots of life out there. Maybe Captain Kirk takes the Starship Enterprise out into space and finds lots and lots of life in the galaxy, but it's all stupid. Okay, that's one possibility. But on the other hand, all the studies that have been done about how intelligence arose on Earth suggest that, well, what drove it was nothing that you wouldn't expect elsewhere. And sure, it took a long time before you got this far, but you needed some preconditions. You needed warm-blooded animals with a high metabolic rate. You needed all sorts of sort of biological developments. And then, in the last 50 million years, which of course is fairly short in the history of the planet, but in the last 50 million years, a lot of species have gotten smarter. It's obviously Homo sapiens, but and obviously our simian relatives, right? Chimps are pretty clever, but birds are pretty clever. Even octopi are fairly clever. Whales and dolphins are fairly clever. There's been an increase in intelligence among a couple of handfuls of species in the past 50 million years. It isn't just one species that got smarter. Now we got smarter than they did, but if you were to visit Earth 2 million years ago, you would have found that the smartest things on the planet were not our simian ancestors, but some white-flanked dolphins. They had the highest IQs, and they didn't leave a lot of literature, but they were the smartest things around. So it does seem that intelligence is actually kind of a fairly natural product of evolution once you get to a certain level of complexity. This is controversial, but at least the indications are that intelligence is not some sort of miracle.
Okay, well, shifting gears a little bit, we also had Professor Dan Wertheimer from the University of California at Berkeley on our airwaves a few years ago, talking about SETI at home. That is, on your home PC, you can get a chunk of this radio data and have your PC via its screensaver basically crunch some of the numbers to look for intelligent signals. What's been the progress for SETI at home in the last several years?
Well, SETI at Home was intended originally just to be a very short-lived project, maybe for a year or two, but it was so popular that it's continued. They expected, maybe 50,000 people, would download this free bit of software so that when they walk away from their computer, it's still humming away, that it would process a certain amount of SETI data that it would download from the servers at the University of California at Berkeley. Well, more than 5 million people have downloaded that software, so that's that's 100 times as many as they expected, and about a third of them use it at any given time. What they do is they distribute a little bit of the data they collect from the radio telescope down in Puerto Rico, the Arecibo radio telescope, which a lot of listeners may have seen in the movie Contact, movie Goldeneye. It's a great movie star. Now, they distribute about 1 or 2% of the data they collect there on the web for people using the screensaver. But the point is that there are so many people doing this with their home computers that it is by far the largest computer project, the largest computer, if you will, in the world right now. And those data are looked at extraordinarily carefully. So, it's really a very, very fine-tooth comb. They look at all the rest of their data right there at Berkeley using, the local Berkeley computers, but they can't look as carefully as they can at this small fraction of the data, which, are the prime data, if you will. Now, has anybody found something? Well, people find stuff all the time, of course. If you do this sort of work, and you're using a big antenna like the one in Puerto Rico, you find signals all the time. After all, you got this huge antenna. It's connected to a receiver that has millions of channels. Of course you pick up signals. But, of course, the question is that ET on the line or is that AT&T on the line? Is it just interference from a telecommunications satellite or something like that? Now, what the guys at Berkeley do is they look at all the signals that have been found by people using their computers at home, and they look for those cases where a signal has been found more than once, in fact, more than twice. If a signal has been found 3 different times, right? Not just by 3 different people, that doesn't count, but by, at 3 different times. In other words, the telescope was pointing at some spot on the sky and they find a signal, and then, 3 months later comes back to that same point. Somebody else finds it again at that same frequency, at that same spot on the sky. If that happens 3 or more times, then they say, hey, look, that's, kind of interesting from a statistical point of view. That suggests it's not just a noise spike. That's, looks like a real signal. And then they will go down to the telescope and will deliberately look at that spot on the sky for a long period of time, for a few minutes, whatever it takes, until they can verify whether the signal's still there. They have done that on several occasions. So far, no dice. But on the other hand, it is quite possible that somebody running SETI at home could, in fact, find the signal that would entitle them to pick up a prize in Stockholm and have dinner with the king.
And that, of course, would be perhaps one of the pivotal events in human evolution on the planet Earth.
I think so.
Well, let me ask you now the $64,000 question. What do you, as an individual, think N is, N being the number of intelligent planetary systems out there, and where are they?
Yes, well, of course, I don't know what N is either, but I tend to agree with Frank Drake, who still works here at the SETI Institute. His office is down the hall from mine. And Frank is now, I guess he'll be 75 in another month or so. But he's still as active as he ever was. And he's a pretty smart guy. He's one of the cleverest guys I've known. And if you ask Frank, look, this is your equation. What do you think N is? He'll say, well, I think it's probably around 10,000. Which is kind of a conservative number compared to Carl Sagan, who thought it was a few million. I think Isaac Asimov thought it was 2/3 of a million. So Frank is saying about 10,000. Well, if it's anywhere between 1,000 and, well, some bigger number, if it's more than 1,000, then that means that the nearest aliens are within, on the order of 1,000 light years, okay, to us. Now, keep in mind that if you looked at the whole Milky Way galaxy, it's about 100,000 light years across. So this is, only like 1% of the way across the galaxy. 1,000 light years. That's far if you're trying to drive it in your Honda, but it isn't so far for a radio telescope. If that's the case, and it really is, it's up for grabs. Obviously, we don't know. But if that's the case, then our experiments should find a signal within the next 20 years, because within the next 20 years, we will have kind of searched stars out to that distance. So that's my bet. But on the other hand, we're not going to know the answer until we know the answer.
And what are your thoughts about, well, where are they? SETI so far has picked up nothing. Is that just a question of lack of sensitivity of the SETI antennas, lack of detectors, or is it because they're shy out there in outer space? Or maybe they don't exist? Or, well, what are your thoughts about why we haven't picked up any messages yet?
Yeah, well, this I think that the answer is very simple. I think it's simply because we've not combed enough galactic real estate yet. But there are people who say, no. The fact that you haven't heard anything yet means something. It means that they're not out there, because any society that was more advanced than ours, and most of them are going to be more advanced than ours. I mean, if intelligence really does occur on planets in a fashion that's not extraordinarily rare, then most of the societies out there will be much older than ours, because, after all, we're the new kids on the block. The Earth has only been here for 4.5 billion years. The galaxy's been around for like 3 times that length of time. So most of the stars out there are older than the sun. So if they're really advanced, then they should have been able by now to maybe colonize big chunks of the galaxy. Who knows? They should have been able to spread around. They should have, remote transmitters. They should be very easy to find. Right? And the fact that we haven't found them sounds like some sort of paradox. In fact, this little argument is often called the Fermi paradox, because Enrico Fermi, the physicist, the Italian-American physicist, was the first to point this out over a lunch at, I think it was Los Alamos in 1950. But in any case, that's his argument. I don't think I buy into that. I don't think it's a matter of them being shy, being coy. Maybe some of them are shy. Maybe most of them are shy. But if only one society has a powerful transmitter out there, then we have a chance of success. I think the reason we haven't found them yet is that we haven't looked very carefully. And all of that is going to change in the next few decades, mostly because of the march of technology.
Well, my personal point of view is that if there's an anthill in the country and you're walking down this country road and you bump into this anthill, do you go down to the ants and say, I bring you trinkets, I bring you beads, I bring you nuclear energy and DNA technology? Or perhaps maybe you step on a few of them.
Yeah, probably. I get phone calls just about every other day from people who have their own explanation of why we haven't heard anything, and it's usually because the aliens are put off by our environmental degradation and our, threatening one another with war and all that sort of stuff. But indeed, I think that from their point of view, none of that matters terribly much any more than whatever wars the ants are getting into concern me. They don't.
Mm-hmm. Now, another stream of thought says that we're looking in the wrong place. For example, take a look at email. Email is compressed, email is broken up and goes through many cities and then recombined at the other end. So if an alien civilization had even a primitive email system, and we were eavesdropping on it, we wouldn't hear much at all. The signals would be compressed in a way that we don't understand. They'd be fragmented and redistributed and reassembled someplace else in a code we don't understand. So we could be listening in to messages that are teeming with intelligent things in it, but we are simply too primitive to understand it. What are your thoughts about that?
Well, I'm sure there's a lot of truth in that. I don't expect that we are going to understand any of the messages, even to the point of being able to sort of break them up into the bits that that make them up. And it's also true that there are all sorts of methods for encoding information, for sending bits around that are fairly sophisticated that we use. For example, your cell phone tends to use what is called spread spectrum technology, where the signal is spread all over the dial instead of being concentrated in one spot. That's very hard to find with a radio receiver unless you know all the details of their communications schemes. So, yeah, there are lots and lots of ways they could make the signal hard to find, but in the end it comes down to this. If they have a transmitter on, that puts a certain amount of energy somewhere in the radio dial, somewhere in the radio spectrum. And we don't worry about how it's encoded or what the message is or anything like that. We don't worry about the message when we do our SETI experiments. We're just trying to determine, is a transmitter on? We're looking for narrowband components to the signal. It's called lots of excess energy, if you will, at certain spots on the radio dial. If we find that, we, of course, don't know what they're saying, whether it's something profound or whether it's something trivial like used car ads. We don't care about any of that. We're simply looking for evidence that their transmitters are on, because after all, that's the proof that we're after.
Okay, now let's talk about flying saucers. Of course, the distances between stars are enormous. It would take the Voyager spacecraft thousands and thousands of years to reach the nearest star. But that's because, we're kind of primitive on this scale that we're talking about. Another civilization could easily be 1 million years ahead of us. And so the next question is there a law of physics preventing a civilization millions of years ahead of us from making contact with us? Is there any brick wall that prevents an advanced civilization from making contact?
Well, Michio, you're the physicist, and you know that there isn't. There's no physics that prevents us. Now, there may be some physics that makes it very hard. Conventional physics, if you use, rockets in the normal sense, the problem there is our rockets, of course, don't go fast enough, but, they're more advanced. They can build better rockets. But when you get up to very high speeds, and you really do need speeds that are comparable to the speed of light if you want to get from one star to the next in less than a century, which sounds to me like something you might want to do no matter who you are.
Well, Seth, we have to take a short break now. Welcome. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is the second half of Exploration. In the first half of Exploration, we explore the world of alien life in outer space with Dr. Seth Shostak of the SETI Institute in Mountain View, California. In the second half of Exploration, we're going to bring on another Seth, Dr. Seth Lloyd of MIT, who's going to talk about quantum computers, perhaps the most exotic form of computation ever conceived. By 2020 or so, we will gradually begin to exhaust the power of silicon because transistors will be so tiny that electrons will leak out of the silicon chip. And we need a replacement. and quantum computers may be it. However, even the CIA is interested in quantum computers. They are in principle so powerful that they could crack any computer code, and you'll be able to eavesdrop on any conversation via a quantum computer. And Dr. Seth Lloyd also entertains the possibility that maybe the universe itself is one gigantic quantum computer. So once again, our special guest today is Dr. Seth Lloyd of MIT, and we're talking about the world beyond 2020. What happens when Silicon Valley becomes a rust belt and we have to go to quantum computers? And now I'd like to introduce our special guest for today. We're very delighted to have with us Professor Seth Lloyd of MIT, author of a new controversial book called Programming the Universe. And the question is the universe a quantum computer? Now, let me explain. We all know that computers that energize modern society are based on silicon. And the silicon chip that you have in your Pentium crams literally millions upon millions of tiny transistors into something that's a little bit bigger than your thumbnail. And the question is, how far can you go until the tiniest transistor becomes the size of an atom? Well, that time is coming. Perhaps in 20, 30 years, we don't know precisely when, but we do know that someday transistors will be so tiny that atoms of silicon simply won't do. We'll have to go to atomic computers, otherwise known as quantum computers, and Professor Lloyd is an expert in this area called quantum computation, and he thinks maybe even the universe is a quantum computer. Now, let me also note that atoms spin like a spinning top, and you all know that spinning tops have an arrow, the axis of spin, and that could point up or down. If it points up, that's a 0. If it points down, that's a 1, and you get binary. But atoms are more than just binary. Atoms can also point sideways and anywhere in between, a superposition of up and down. And that's where we get into the bizarre world of the quantum theory, where you don't really know quite where this arrow is pointing, but you have much more freedom than simply zeros and ones. You have zeros and ones and in between. These are called qubits, or quantum bits. And Dr. Seth Lloyd is one of the world's experts in this new area. And of course, many people are interested in this. Modern technocrats are interested because one day quantum computers may have the internet on it, and as well as banking records and your credit card records, not to mention the fact that the CIA wants to get their handle on quantum computers because with it, you can crack any code with a quantum computer. But you see, Dr. Lloyd goes even farther than that, because you see, everything around us is governed by atoms. Atoms, in turn, obey quantum mechanics, and therefore he claims that the universe is one gigantic quantum computer. And if that's true, then what is it computing? What's the program? Who wrote the software? God? I mean, your mind starts to go crazy thinking about the possibility that maybe the universe is a quantum computer. So once again, our special guest today is Dr. Seth Lloyd, author of the new book, Programming the Universe. Professor Lloyd, tell us a little bit about your youth. Were there any kinds of incidences or stories you'd like to tell about what set you off in a career in mathematics, computational physics, and physics?
Well, I always loved fooling around with numbers and with games and things involving geometry when I was a kid. I played a lot with blocks and would build huge geometric constructions as well as buildings with them. And then when I went to school, I was amazed to find out that there was a subject called physics where with relatively simple math, you could discover a huge amount about the way the world works. Of course, then I went to graduate school and found it was really the opposite. There's a huge amount of complicated math, and you only understand a little tiny bit about the way the world works. But by then it was too late. I was suckered into the field.
And you also mentioned in your book that as a graduate student, everyone seemed to be doing string theory, but you saw your destiny going in a slightly different direction. Could you elaborate?
Sure. When I when I was at Cambridge University, I did a MPhil in History and Philosophy of Science and started working on ideas of information and quantum mechanics. I also studied quantum gravity with Stephen Hawking. And it struck me that there was a connection between these two things, these two ideas of quantum information and quantum gravity. So when I went to Rockefeller University to work with Heinz Pagels to do a PhD in physics, I started off working on ideas of quantum information and quantum gravity, basically the same thing that I'm doing today. Unfortunately, they didn't like that very much at Rockefeller University, and about halfway through they told me I better cut it out and work on something more conventional like elementary particle physics or string theory.
Well, I guess reality intrudes. And Heinz Pagels, I should also mention, was one of the early guests on Exploration, speaking about elementary particle physics. Now let's talk about things that are very practical. The average American, of course, says, what's in it for me? Numero uno. Am I going to get better internet reception? Am I going to get better computer power? So let's talk about computer power, computer games, and what we have for Christmas. Everybody knows that at Christmas time, your computer is almost twice as powerful as the computers of the previous Christmas. And that's called Moore's Law. So some people say, well, Moore's Law is going to go on forever. However, you think otherwise. So tell us a little bit about Moore's Law and why you think Moore's Law is going to break down. So by Christmas time, we're not going to get Christmas presents that are almost twice as powerful as the previous Christmas.
Well, it's dangerous to predict that Moore's Law will break down. People have been predicting its imminent demise for decades, starting in the late 1960s. And every time some clever engineer managed to find a way around whatever specific problem seemed to be standing in the way of progress. And in fact, if you look at Moore's Law, it's not just one technology that has made computers get more powerful by a factor of 2 every year and a half or so. It's a whole series of technologies that have kicked in, from vacuum tubes to transistors to integrated circuits. And these technologies rely on the improvement, the rapid improvement of other kinds of methods like machining, material science, etc. So Moore's Law is kind of the tip of the iceberg of this rapid improvement. However, it can't actually go on forever for a simple reason, that is that computers are governed by the laws of physics. And the laws of physics tell you how small you can make things and how fast you can do things. And so if you actually took all the energy in the universe and turned it into a gigantic computer, a possibility envisaged by Isaac Asimov in his story, The Last Question, I was able to calculate using the physics of information processing how big such a computer would be. And, this computer, this universal computer, if you like, up till now it could have performed about 10 to the 120 elementary operations, or ops, on about 10 to the 90 bits. And if you actually look at the exponential progress of Moore's Law and ask at what point could the whole universe become a computer, it's only 250 or 400 years away. So even if we manage to take every elementary particle in the universe and turn it into have it participate in a computation, then Moore's Law couldn't last for more than a few more centuries.
Okay, well, let's be very practical. On your desk is a laptop with a Pentium chip, let's say, and that Pentium chip has a layer of chemicals, the smallest layer being 20 atoms across. 20 atoms across, the smallest layer in a Pentium chip on your desk. In 20 years, in fact, less than 20 years, that layer will be 5 atoms across at the rate at which we're going. 5 atoms across. And at 5 atoms, we have to introduce something called the Heisenberg uncertainty principle, which says you don't really know precisely where that electron is. In which case, if electrons leak out of the layer, your Pentium chip just short-circuited, and your laptop is now useless. And so the question is, how small can you make a transistor before you bump up against atoms, and at the atomic level, everything's uncertain.
Yeah, well, that certainly is something to worry about. And indeed, if Intel starts making chips where the electrons are just leaking out all over the place, the chips wouldn't work. So they clearly can't make them by exactly the same design. However, there's certainly nothing wrong with, or nothing against the laws of physics to actually store bits of information at the atomic scale. Indeed, one atom, one bit. And as the components of computers get smaller, indeed, quantum effects like the Heisenberg uncertainty kick in. But maybe we can actually take advantage of these effects like the Heisenberg uncertainty principle. Maybe we can turn it from being a bug into a feature. And indeed, that's what my colleagues and I do when we try to build computers whose feature scale, the size of the bits, are down at the level of individual atoms.
Okay, now let's talk again very practical things when people say, what's in it for me? Well, the government, of course, would ask the same question, what's in it for us? And let's now talk about the CIA. The CIA, of course, is very much interested in breaking codes. They love to break the codes of other nations. But many times, to break a code, you have to have a key. And sometimes this key is the ability to factorize a huge number. Let's say I have a number with 100 digits. Take a sheet of paper and write a random set of integers 100 digits long, would fill up many, many sheets of paper. And then you were asked to factorize it as the product of two numbers. Well, how would you do that? It would exhaust most computers, and some people therefore think that certain codes are safe, that it's beyond the ability of most ordinary computers to crack the factorization of a number that is 100 digits long. But now let's talk about computing on atoms. Is it possible that this new generation of computers, this quantum computers that you are pioneering, could be able to crack codes that even the CIA cannot crack?
Well, it's possible, and indeed, if we could build a quantum computer, a computer that stored bits of information on individual atoms, one with only a few tens of thousands of quantum bits, and one able to perform a few 100 million operations, which is to say something quite piddling compared with the laptop on my lap right now. If we could build a very small quantum computer, then we could use these kind of weird features like the Heisenberg uncertainty principle to compute in a different way. And indeed, in 1994, Peter Shor, then at AT&T, now at MIT, showed that, in fact, you could exploit quantum weirdness to factor large numbers and break these codes with even a rather small quantum computer.
Okay, now let's talk about computers themselves. Everyone talks about the digital age. Everything is digital. But what does digital mean? And what is this zeros and ones that sometimes we see in the press? And like if you saw the movie The Matrix, you saw a bunch of zeros and ones. What are these zeros and ones? And what is the so-called digital age?
So a 0 or 1 is what's called a bit. A bit is the smallest possible chunk of information. And it doesn't have to be 0 and 1. The famous bits are yes or no, heads or tails, true or false, black or white. Essentially, any thing that can take on two different states, two different distinguishable states, registers a bit. And that's the smallest chunk of information. And the way that digital computers work is they break up information into bits, into its smallest chunks, and then process it that way.
Okay, so if modern society, the wealth of nations, everything we see around us, if it's governed by zeros and ones, then let's now talk about qubits, quantum bits, where atoms don't have to be in zeros and one states. They could be zeros and ones and in between. So tell us about how atoms can be in between 0 and 1.
Yeah, as soon as one starts talking about quantum mechanics, then things start to get weird. Niels Bohr famously said that anyone who can contemplate quantum mechanics without getting dizzy hasn't properly understood it. But let's go on anyway. Back essentially a little more than 100 years ago, physicists including Max Planck, Einstein, Niels Bohr, and others realized that there was an essential chunkiness to nature, a kind of a digital quality, that things that people thought of as being wave-like, like, for instance, light or sound, came in little chunks. Light came in little chunks called photons, a little particle of light. Sound came in little chunks called phonons, a little particle of sound. And so at this quantum level, things that look continuous actually are somewhat digital. For instance, you could have no photons in a spot or one photon in a spot. Or you could have one electron over here or one electron over there. And indeed, that's how a conventional computer registers bits, though with a lot more electrons. So, bucket empty, lots of electrons out of the bucket, that's 0. Bucket full, lots of electrons in the bucket, that's 1. Now, in quantum mechanics, so quantum mechanics says the bottom of the world has this digital feature, which is good because that means we can use this digital nature of the world, this quantum nature, to store digital information. But there's another weird feature of quantum mechanics that goes under the name wave-particle duality. So just as waves like light are made up of particles, so things like particles, like electrons, for instance, have waves associated with them. The wave is, an electron's wave tells you something about where the electron is. Now, so in a digital world, an ordinary bit, you could either have an electron here, that's 0, or there, that's 1. But in the quantum world, the electron's wave can be both here and there at the same time. So a quantum bit, electron here and there at the same time, is a bit that can register in some funky quantum sense that nobody really understands, 0 and 1 at the same time. Qubits are not either 0 or 1. They can be 0 and 1.
Okay, so let's take an analogy of a top, a spinning top. Everyone's played with them as children, and atoms spin, and therefore atoms are also like spinning tops, and atoms can spin either up or down when they're placed in a magnetic field, or at least until the quantum theory came in. And so now we can have tops that spin up, tops that spin down, and tops that spin in between. Now, these qubits, these quantum bits, can be between 0 and 1, and they consist of atoms now, not molecules of silicon that you see on a transistor. So how would you actually now build a quantum computer? Let's say that you were an inventor, have access to laser beams and magnetic fields and the ability to play with atoms, individual atoms. How would you build a quantum computer?
So I guess, in fact, a little more than 10 years ago, I was in that position because quantum computers, the idea you could compute at the level of atoms using quantum mechanics, have been proposed by Paul Benioff and Richard Feynman back in the 1980s. But until by the early 1990s, nobody knew how to build one. Nobody had a clue. And around 1992, 1993, I realized that with off-the-shelf elements like lasers and microwave generators, you could take atoms and make them compute. And the way the type of computing I suggested was, in fact, just what you suggested. We'll take spin as our bit. So spinning up, or we can call that clockwise, is a 0, and spinning down is a 1. And then spinning sideways is this funky state of a qubit, 0 and 1 at the same time. So now, if you take such an atom, the spin of the nucleus of an atom, you put the atom in a magnetic field, and then you zap it with microwaves, you can make that bit flip. This is called magnetic resonance. It's the same technique that you use to image your knee when you blow it out while skiing. So if you put on light or microwaves at just the right frequency, it will tickle the nucleus and cause the nucleus to flip. First, it will start at, let's say, it starts at the state 0, or spin up, and then it gradually rotates down through the state spin sideways, 0 and 1 at the same time, to the state spin down, or 1. Now, if you have lots of atoms, lots of nuclei, you can address them with different frequencies. You can think, in fact, of these different atoms as essentially listening to different radio stations. So, if I have one atom that listens to 89.7 megahertz, WGBH here in Boston, then a second one, say the first one is carbon, say the second one is hydrogen, will listen to WCRB, 102.5. And when I address these two atoms with microwaves of different frequencies, or radio waves of different frequencies, then if I shine light at 89.7, the carbon atom, which listens to 89.7, will flip. And if I shine light or microwaves at 102.5, then the hydrogen atom, which listens to WCRB, will flip. So I can address atoms individually. And then if you're sensitive to the interaction between the atoms, you can massage those interactions to make up logical operations. For instance, causing the hydrogen atom to flip if and only if the carbon atom is spin down or 1. And since at bottom, a computation is nothing more than making bits flip, and making one bit flip if another bit or several other bits, say, read 1, then any computation can be broken down into these simple operations, making bits flip, making them interact with each other. And the atoms in our molecule, the carbon and the hydrogen, can perform a simple computation simply by addressing them with light.
Okay, so let's back up a bit. You have a bunch of atoms, let's say in a line, and you place it in a magnetic field, so the spins are either up or down, or perhaps sideways, a mixture of up and down. And once you have these atoms aligned, then you hit it with microwaves, and at certain frequencies, the atom will absorb the radiation and flip.
That's right.
And each flipping process represents a calculation. Now, because the atom is neither up nor down, but it's a mixture of up and down, you have much more flexibility than in zeros and ones. Okay? Now, then the question is, what kind of computation can you perform on this? Can you do the calculations of a laptop? Can you do 1 + 1 is 2? What's the world's record for computing on these atoms?
So you can certainly take these atoms and make them do anything that an ordinary digital computer could do. So at the moment, because atoms are very small, and even if you extrapolate Moore's law into the future, depending on how you calculate size, then it will take 25 to 40 years for us to get computers where the components are atomic, even if Moore's law continues at its current breakneck pace. But the quantum computers we've built can do anything that an ordinary computer, say, with 7 to 10 bits can do, because that's the size of the computers we're looking at right now. However, so as viewed as classical computers, just doing ordinary operations like 1 + 1 = 2, then they're pretty weak, these quantum computers. Not only are they small in actual size, the size of a small molecule, but they're small in terms of power. However, if we start to take advantage of the ability of atoms to read 0 and 1 at the same time, then quantum computers can do things that classical computers can't. And the secret comes from looking at what bits can do in a computer. So bits can store data, but they also can be instructions. So 0 could mean do this, right? And 1 is an instruction meaning do that. Now, if I take a quantum bit, a qubit, that reads 0 and 1 at the same time, and I feed it into a quantum computer as an instruction, then the quantum computer will do this and it will do that at the same time. So quantum computers can multitask or do parallel computation in a way that classical computers can't. And that's why if we could build a quantum computer, say, with a few tens of thousands of quantum bits, which is difficult, but certainly not impossible, then we might be able to start striking fear into the hearts of the CIA, the NSA, and other three-letter agencies.
Now, the reality, and correct me if I'm wrong, the reality is that the world's record for a quantum computation is, ta-da, drumbeat, 3 times 5 equals 15. And I understand that that calculation was done on something like 5 to 7 atoms. So correct me if I'm wrong, but at the present time, we're still at doing calculations that even children can do.
Tiny steps for tiny bits, Michio.
Mm-hmm.
You've got to start from somewhere. And indeed, as you pointed out, the whole notion that quantum effects might come into play strikes fear into the heart of Intel. So we have to figure out how to make atoms compute. And before we start to make Avogadro's number of atoms compute. So, starting about 6 or 7 years ago, we started to do the first quantum computations, and we've been gradually making them bigger. It takes a tough engineer to handle a tender atom. Atoms are small and sensitive, and as I say, we're not even due to make atomic-scale computers for another 25 to 40 years by Moore's law. So it's hard to do. But we do have some progress. For instance, if we're not looking at general-purpose computation, like multiplying 3 times 5 to get 15, if we look at special-purpose computations, like trying to simulate other quantum systems, then Feynman pointed out in the early 1980s that quantum computers might be very good at that. And indeed, we've built special-purpose quantum computers that contain more bits than any classical computer on Earth, 1 billion bits. And we've used these to simulate effects like quantum chaos or the behavior of electrons hopping around in aside metals that you could never, ever do even with the world's largest supercomputer. So, our computers are small we're only factoring very small numbers right now, so I think the CIA can rest in peace for a decade or two. But we can still do some things that even the largest classical supercomputers can't do.
Well, I'm afraid that's it for Exploration. Once again, our first special guest was Dr. Seth Shostak of the Search for Extraterrestrial Intelligence based in Mountain View, California. And the second special guest was Dr. Seth Lloyd of MIT, an expert on quantum computers. And if you want a copy of today's program, call the Pacifica Program Service at 1-800-735-0230. That's 1-800-735-0230 for a copy of today's program. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics, inviting you to join us every week for a discussion of science and its impact on society. Good day.